So continuing on, when we're talking about a rational function, the other feature that it can have is a horizontal asymptote. So if, as x gets very large or very small, the values of the function, the y values, approach some fixed number capital L, then the line y equals capital L is a horizontal asymptote. And again, you never have to write out horizontal asymptote again. You can use HA of the graph of R. So if as x gets very large, the graph is approaching some number capital L on the y-axis, then y equals L is a horizontal asymptote of the graph. So for our previous example, the 3 over x minus 1 plus 2, we can see that we have a horizontal asymptote of y equals 2. So a horizontal asymptote, when there is one, describes what's called the end behavior of the graph as x gets very large or very small. So this is an important point, that the graph of a rational function may intersect a horizontal asymptote. You have to check for this. So the graph can do things like this and cross the horizontal asymptote and then come back and approach it. So a vertical asymptote, when there is one, describes the behavior of the graph when x is close to some number c. So this is the vertical asymptote. The graph of a rational function will never intersect a vertical asymptote. It can only ever approach it this way or approach it this way. And on this side, it either approaches it this way or approaches it this way. Those are the only behaviors the graph can have. So there is one more behavior we need to investigate. As x gets very large or very small, the graph of the rational function may approach a straight, slanted line. The function looks more and more like some line y equals ax plus b. So when that happens, we say you have a slant asymptote, and the graph is approaching that oblique or slant asymptote. So this only describes, again, the end behavior of what's happening over here when x is very big and x is very small. The graph of a function may intersect an oblique asymptote. So here's an illustration of an oblique asymptote. And I'll talk in a minute about when you can tell that's what's going to happen. But in this case, we have x cubed plus 1 over x squared minus 5x minus 14. So what we can tell about this graph is that the numerator is growing faster than the denominator, but not very much because we have a cubic over a squared. So what we need to do is polynomial long division. And if you don't remember how this works, let's do it really quickly. You have to have placeholders for any degrees that are missing. So you have x cubed plus 0x squareds plus 0x's plus 1. You're dividing by x squared minus 5x minus 14. So you put an x up here and then multiply and get x cubed minus 5x squared minus 14x. And then you subtract. Subtracting means to change all the signs and add. So these x cubes cancel out, and I'll have 5x squared plus 14x plus 1. And then I have plus 5. And again, distribute, get 5x squared minus 25x minus 70. And subtract, which means to change all the signs and add. The x squareds cancel out. I get 39x plus 71. So another way of writing this function is that it's x plus 5 plus 39x plus 71 over x squared minus 5x minus 14. Well, this part, as x goes to infinity, this goes to 0. Do you see why that would be? The degree of the bottom is larger, and so that denominator is going to get bigger and bigger much faster than the numerator. So the graph looks more and more and more like y equals x plus 5, a line that we know how to draw. So once the rational function is in lowest terms with no matching factors in the numerator and denominator, so you got to make sure and look for that, then real zeros of the denominator tell us where to find vertical asymptotes. So denominators go with vertical asymptotes. So a rational function, r of x equals p of x, a polynomial, over q of x, a polynomial, in lowest terms, will have a vertical asymptote x equals r if x is a real zero of the denominator, q. So another way of saying this is if x minus r is a factor of the denominator, q, of a rational function, r of x equals p of x over q of x in lowest terms, then r will have the vertical asymptote x equals small r. So we're asked to find the vertical asymptotes of the rational function, and what we're being asked is find when the denominator is 0 once you're in lowest terms. Well, this is in lowest terms. 4x squared doesn't factor anymore. So I want to know, when does x cubed minus 1 equal 0? When does that happen? So it happens when x cubed equals 1. So we can take the cube root of both sides and say that happens when x equals 1, and that's the only time it happens. So we have a vertical asymptote at x equals 1. This function we're going to look at a little harder because it's a little more complex. So here's a little note about multiplicity and vertical asymptotes. There's only 4 kinds of behavior, actually, so study these because these are the only 4 things that can happen at a vertical asymptote. So it might seem like a million different things can happen, but actually these are the only possibilities. So you need to memorize these and have them firmly in your mind. Okay, so everything we need to know about whether a function has a horizontal or oblique asymptote can be found by checking the degree of the numerator as compared to the degree of the denominator. And remember, degree is highest power on x that you see. So there's 3 possibilities. We could have the degree of the numerator is bigger than the degree of the denominator. So if we had x cubed minus 2x plus 3 over x minus 4, then the result is no horizontal asymptote, no oblique asymptote. Okay, if the denominators are and the numerator have a big difference between their degrees and the top is bigger, think about what happens as x gets very large. The numerator is going to get way bigger than the denominator, so the ratio is going to get huge, and the graph keeps growing. The y value gets higher and higher. No asymptote. So then we could have the degree of the numerator is equal to the degree of the denominator. So that could be, what if we have 2x cubed minus x plus 5 over 3x cubed plus 7. And then what happens is you get an HA. In this case, y equals 2/3. It's the ratio of the leading coefficients. So you need to know those vocabulary words. So it's the ratio of the leading coefficients if the degrees are equal. And then you could have the degree of the numerator smaller than the degree of the denominator. So if you have x plus 1 over x squared plus 2, now you can see the denominator is going to grow a lot faster. And the result is you have a horizontal asymptote of y equals 0, which is the x-axis. So I did these in a different order than when I wrote the note. So a fourth case arises. There's a special case of number 1. If the degree of the numerator is 1 more than the degree of the denominator, then you end up with that oblique asymptote. So if you have x cubed plus 2x squared minus 7 over x squared plus 3x plus 5, then you get an oblique asymptote if the degree of the top is 1 more than the degree of the bottom. So then we'll do these examples together to find any asymptotes, and that's the end of the section.